Well, guess what? We're going to talk about more alcohol reactions. Aren't you excited? Yeah, I told you. It's over and over and over, folks. I mean, it's one reaction after another when it concerns the alcohol theory. And you're quickly seeing that add up with the substitution and elimination versions that are out there that we've already discussed. So, in this lecture, we're going to start a new section of the alcohol reactions. No more substitution. Well, there is substitution involved. They just don't label it as a formal substitution. And no more elimination either. So this section is going to concern what we call the oxidation of alcohols. Now, what does oxidation actually mean? Well, this is always a hot topic in organic chemistry. Oxidation reduction. Oxidation reduction. Does that ring a bell? Well, if you took a General Chemistry 2 course, you probably went through a moment in time where you talked about reduction and oxidation reactions. Do you remember those? And we shorthanded that to something called redox. Red, of course, is reduction, and OX is oxidation. So, in that theory of general chemistry, they said, oh, well, they probably gave you a little analogy. Leo goes grrr. All right, so Leo the lion, loss of electrons is oxidation, hence the O, and grrr, G is gain, electrons is reduction, and hence the R. So they went through a moment and they probably tied this to batteries and electrochemistry. If they taught it the proper way, that's what they should have done. So electrochemistry, the electron flow diagram, moving from one side to the next, providing us movement, providing us energy, hence how batteries work, was all redox driven. Loss of electrons and gaining of electrons. Okay, well, guess what? All of this. No. Organic doesn't really like to use those definitions. Why? That's just organic for you, folks. So I basically led you up to believe that it was going to be the same thing, and actually it isn't. It's related. It's related. I can make the argument that it's pretty much the same thing, but that is not how organic, especially your organic text, will present this information. So in oxidation, it's a little bit easier. Oxidation, you see the word oxygen in here, right? So in organic chemistry, very often, when we talk about oxidation reactions, we are going to be increasing the number of carbon to oxygen bonds. Is that a little bit easier? I hope it is. Electron mess, electrochemistry, galvanic cells. Come on now. Oxidation in organic means you look at the oxygen, and if you increase the number of C to O bonds, this is going to be classified as an oxidation reaction. Now, this is not the only thing that classifies as oxidation. I just want to make that clear, but it suits our purposes for now, and that's really what matters. So, for instance, if I have a carbon to an oxygen bond, and maybe that oxygen also has a hydrogen with it, hence, ding ding, alcohol. And if we undergo a reaction where we increase the number of C to O bonds, then we have just performed an oxidation reaction. Now, the problem here is you're going to look at this oxygen and you're going to say, well, no, wait a minute, oxygen can only have 2 bonds and you've just drawn a third one. I know. So we have to get rid of something. And what we get rid of is that hydrogen there. So this is an example of an oxidation reaction. The number of C to O bonds will increase. By definition, that is oxidation, and this is the section of organic reactions that we're going to concern ourselves with when it comes to alcohols now. So we're going to have some reagents. We're going to have something in order for this reaction to take place, right? And we're going to talk about a few of options that are out there. Again, why the options? It's because some of them might not be as user-friendly as some of the others. Now, here's the thing with oxidation reactions. They work great with primary and secondary alcohols. They work great for those. And here's why. A primary alcohol is an oxygen, an OH, that's attached to a carbon that's really only attached to one other thing. That's it. A secondary alcohol is an OH group that's attached to a carbon that's attached to two other things. Other carbons. That's what I'm talking about, right? We know that they're going to have hydrogens. We know that that's there. I'm talking about other carbons. But what about tertiary alcohols? All right, so tertiary alcohols are OH groups on a carbon that has three other carbons at least attached to it. Now, they can have more, right? So I can put on here R, or I can go squiggly on each side. Well, that means they continue on. And the same thing happens with the tertiary. These things can go bigger if that's what they want to do. It's not a problem. But there's got to be a reason that primary and secondaries undergo oxidation pretty well, but tertiaries do not. Do you know why? Can you look at these structures and tell me why oxidation does not happen with tertiaries? No tertiaries when it concerns oxidation. Why not? Well, let's think about this for a minute. I just told you that an oxidation reaction increases the number of carbon to oxygen bonds, right? Let's not worry about the oxygen. Let's worry about the carbon. Look at the primary. If I add on an extra bond here for an oxidation reaction, this carbon now has 1, 2, 3, and then 4 from the hydrogen. That hydrogen goes away to make room for a double bond. If I look at the secondary, well, this carbon already has 3 bonds, doesn't it? And that fourth one that's not drawn is to a hydrogen. So if we can remove that hydrogen, remember they're disposable. Nobody wants the hydrogens. And if we can make room for a double bond, there we go. We can remove that hydrogen in order for that to happen. We've increased the number of carbon to oxygen bonds. Now let's take a look at a tertiary. In the tertiary route, we have a tertiary alcohol. We need to increase the number of C to O bonds for oxidation. So if we increase the number of C to O bonds, look, that carbon doesn't have a hydrogen that's easily disposed of. It has 3 other bonds to carbon. And the fourth one went to the OH group, and a fifth one went to an OH group. No, this is not going to happen. And that's the problem. Tertiaries have no spot for an extra bond between the carbon and the oxygen. It gets overloaded. And because of that, they do not undergo oxidation reactions. All right, so there's a little bit of intro with oxidation as far as we're concerned when it concerns alcohols. More details. What kind of reagents are required here? Typically, there's just one, pretty simple, actually. It's just chromic acid. That's it. There's a couple of different ways to get chromic acid. Sometimes they're really nice to you, and they'll just write out chromic acid. Other times they are trying to tell you how they're making the chromic acid. And there's 2 different ways that the textbook typically represents this. But just look for the chromium. And if you can look for the chromium and you see the chromium, just pretty much take a guess that this is an oxidation that they're trying to get you to go after. So a couple of ways that we could do this, we could take what we call chromium, trioxide. We could dissolve that into solution, and that solution is made up of some acid. And that acid could be something like sulfuric acid. Or what we could do is we could take a sodium or a potassium dichromate solid, very pretty, very colored, and we could also dissolve that into some acid. So they're either going to tell you full-blown, straight-out chromic acid is used in the experiment, or they're going to try to trick you, and they're going to try to use one of those versions in the wording or within the reagent structure. Chromium trioxide or sodium/potassium version of a dichromate. And both of those do the same thing, folks. It somewhat basically generates chromic acid in solution. That chromic acid reacts with the alcohol in order to oxidize it and give us a product. So I don't want the actual reaction to throw you for a loop here. That's all that they're trying to do. I'm going to see chromium in either one of these versions, aren't I? I'm going to see chromium in the dichromate. I'm going to see chromium listed in the chromium trioxide, or I'm going to see chromium listed in the chromic acid. Whichever version they throw at you, it's oxidation. You increase the number of C to O bonds. What kind of products get formed from this reaction? Okay, so let's take a look here. Let's say that I've got a primary alcohol. So I'm just going to draw it like this. All of these other carbons have hydrogens on them to make them happy, but once again, I leave those off. They're understood to be there at this point, okay? And then down here below, we'll do a secondary alcohol, and I'll just draw the OH there. All right, so here's my primary version. There's the secondary version. So if the number of C to O bonds increase, what happens is that in the product, we're all bye-bye hydrogen, and what we form is an extra C to O bond. And guess what? The secondary does the same thing. Bye-bye hydrogen, and we form a extra C to O bond. Did you see how easy that was? It's painless. It's really pretty much all you got to do. The issue here, though, is not what kind of product gets formed, like this, structure-wise, but what functional group was formed. And depending on what you did in Chemistry 251 or Organic Chemistry 1, well, you might be comfortable with these functional groups and you might not. So one of the things that you need to understand is that this carbon has 3 bonds. The fourth one, though, that's not drawn is understood to be a hydrogen right there. Just like there's 2 hydrogens here and 3 hydrogens there if that's where this molecule stops. And then in the secondary version, same kind of thing. This first carbon has 1 bond right now, so there's 3 more to hydrogen. I can draw those there. And this carbon in the middle doesn't have any because it has 4 bonds. And this carbon on the end, well, it's got 1 bond, so it needs 3 more hydrogens. So I can add those if that makes it easier for you. And these 2 things are different functional groups. You know, alcohol is OH, and OH is a functional group on a molecule. And here we have representation of 2 others. So if you oxidize a primary alcohol, you will end up with a carbon double bond O. But you got to keep in mind, primary means that oxygen is at the end. So this functional group, carbon double bond O at the end, which means hydrogen on one side. That's the key, that it's on the end of the molecule. That functional group is called an aldehyde. So a primary alcohol is oxidized to an aldehyde. Now, we did not go through how to name aldehydes in Organic Chemistry 1. So I'm not going to make you name aldehydes here because you don't know how to do that yet. But we did at least pinpoint this functional group and identify it. Now with the secondary version, a secondary alcohol will oxidize. I can see that carbon's in the middle. That carbon does not have hydrogen on either side of it. So this C double bond O with an R group to the left and an R group to the right, R means any random R group, means that this C double bond O is in the middle of a molecule somewhere. It's on the inside, not on the outside, not on the end. And this is called a ketone. So a carbon double bond O with something on the left and something on the right. That's a ketone functional group. Primary alcohols oxidize to aldehydes. Secondary alcohols oxidize to ketones. This is the thing that we're going to have to keep straight because, as you can see, it was very easy for me just to say, oh, erase a hydrogen, draw an extra bond. There you go. There's my answer. But sometimes they might not just want that. They might want you to label it as an aldehyde or as a ketone functional group. And now you know what those functional groups are supposed to be. Now, the issue here, another issue that we have with oxidation, are with the stinking primaries. Because, folks, they can go on and they can oxidize again. What? What do you mean they can oxidize again? Oh, look at it. What did I just say? I said that we take a carbon, erase a hydrogen, and add on a bond. There's my double. We did the same thing down here. We took off the hydrogen from the alcohol. Bink, away it goes. We added on a bond, and we formed the oxidation reaction product. Look at the primary, though. Look at this. It has another hydrogen. Well, the secondary doesn't have one, does it? No, it doesn't have any. I cannot go in and rip off a hydrogen from a secondary oxidation product because there's not a hydrogen to rip off. But there is one with the primary group, and it's right there. So primaries can actually oxidize again. There's a way that we can stop it, though. And I'll tell you how to stop it in just a second. But if it is allowed to go to completion, what happens here? I've got the carbon and the carbon and the carbon, and I just formed this double bond O, right? Okay, well, I can't have a C triple bond O. That doesn't make any sense, does it? Oxygen only needs 2 bonds. It doesn't want 3. Every time it's made 3, it's just completely gotten rid of it, and it is reverted back to where it came from. So this carbon knows, first, it has 4 bonds. Something's got to be removed to increase the number of C to O bonds here. Second, the oxygen that's currently there, it doesn't want any more. And it's going to say, no, carbon, you need to stop. Leave me alone. You're being very aggravating right now. And carbon listens, because carbon gets pushed around. Oxygen's a big old bully. That's all it is. So the only way that we can increase the number of C to O bonds here is if we do it on this hydrogen side. And that's exactly what happens. So the primary alcohol will first oxidize to an aldehyde. And if you let it keep going and do nothing about it, it will oxidize again because of that disposable hydrogen that's right there on that carbon. This hydrogen, beep, goes away. And we need to increase the number of C to O bonds, right? And it happens because an OH group will go on. Now you're looking at this OH group and you're saying, whoa, wait a minute, that's an alcohol. So we've started with an alcohol and then we've oxidized it to an aldehyde and now we're oxidizing it again back to an alcohol? The answer is no, not quite. That's not really an alcohol because that OH group is attached to a carbon with a double bond O. Just like this hydrogen was on a carbon with a double bond O. And then this carbon was on a carbon with a double bond O. When this happens, this is a special type of functional group. It is not an alcohol. This is called a carboxylic acid. And just like an acid, it satisfies the name. It can donate protons into solution under the right pH value. Now, those protons that it will donate, where do you think they're going to come from? Yeah, right there. That's the little hydrogen that will be spit off into solution when it doesn't want it anymore. So there's got to be a way to stop that process from happening because maybe I don't want to make a carboxylic acid. Maybe I want to use a primary alcohol, oxidize it, get an aldehyde, and maybe I want to stop it there. And I can do that. And we'll talk about that in just a second. So there is a key step that I can throw in here that a lot of people get confused on why we use it in the first place. But now you know. So let's take a look at some examples. Let's take CH3 and then CH2, CH with an OH group up there, and a CH3. And let's react this with CrO3H2SO4. And they tell you, what is the product? Well, you're going to look at this question and you're going to go, chromium. There it is. There's my chrome. Not the chrome that's shiny bling bling on the wheels on the cars, folks. This is a different type of chromium. It's a poison chromium, if you're not careful. Oh, that's not what we put on our cars. Make it shiny. Oh, it's not. It's a little different. So this is a very good example of an oxidation reaction. Oxidation means increase the number of C to O bonds. And you go, oh, okay, I know where my O is, so I know how to increase that number of C to O bonds. So you write down, just like before, the reagent that you started with. This is where I always start. There you go. Not too much is going to change here. So if you increase the number of C to O bonds, you're going to go hydrogen. You're disposable. Bing! There you go. And we increase the number of C to O bonds by drawing an extra line. Okay, well, I got a little happy there. That shouldn't be a 2. That should be a 1 hydrogen. So you're looking at this right now and you're going, well, wait a minute. In the reagent up here, we have a carbon to an O. There's 1 bond. A carbon to a carbon. There's my 2nd bond. A carbon to a hydrogen. So there's the 3rd bond. And then the carbon to another carbon. So there's the 4th bond. So that looks pretty happy. So I'm okay with that, right? The molecule's okay with that. Carbon should have 4 bonds, and it does. But down here, when I erased the hydrogen from that point and I drew an extra line, let's look at what happened here. The oxygen has 2 bonds. That makes it happy. That was chemistry 251 stuff. This carbon, though, has 2 bonds to oxygen, so there's 2. Then it has a bond from carbon to carbon, so there's an extra one, which is a total of 3. And now it's got this carbon to hydrogen bond that I had before. There's a total of another one, so that's 4. And then it has a carbon to carbon bond rounding out the right-hand side. And that's another bond. That's 5. Can't have 5. So there's got to be something else in the mechanism Because the hydrogen that's on that carbon to allow that double bond to form has to be removed. And that is how that carbon gets 4 bonds in total. So not only are we erasing the hydrogen on the alcohol group, but we're also erasing the hydrogen that's on the carbon involved in the oxygen bond. Remember, tertiaries cannot do this, and the reason is because they do not have a hydrogen that can go away. That is why that happens. So this is a secondary alcohol, and this secondary alcohol here has made a ketone, and I know it's a ketone because C double bond O, and there's something on the left and there's something on the right. So there's your first example of an oxidation. So let's do another one. This time, let's focus on a ring. And off this ring is an OH group. And we're going to react this with Na2CR2O7H2SO4. That's what they're thinking. We're going to get them with this one. Well, don't let them get you, because these reagents, I see chrome right here, and chrome means you're going to increase the number of C to O bonds. Okay, if I just need to increase the number of C to O bonds, then I'm going to take my ring structure, and here's the OH group that's there. So the rules say oxidize, increase the number of C to O. So what I simply have to do here is erase the hydrogen. Bing, there it goes. And then I'm going to pretend to erase the hydrogen on that carbon that it's attached to. Bing, there it goes. And that opens up a site of attachment that I can put my double bond. And there you go. There it is. This is a secondary alcohol, OH, onto a carbon that's attached to 2 others. Therefore, my product is a C double bond O. That's carbon on one side, carbon on the other. That's a ketone, just like the rules tell me. Let's do another example. While we're on a roll, this time let's do a cyclopentane ring. And this has a CH, maybe here, OH, CH2, CH3, and we're going to react this with H2CrO4. Okay, well, I'll look at this reaction and I go, chrome. So that means oxidation reaction happens. I need to increase my number of C to O bonds. Okay, so I'll take my reagent, here is my cyclopentane, and I'll just redraw the whole thing perfectly fine. That's why you're using a sheet of paper and a pen. Now use it. And the rules tell me oxidation increases the number of C to O. So the only way that this is going to happen is if I erase that hydrogen and I erase the hydrogen there, that opens up a site of attachment, and bink, there you go. There's your C double bond O. This OH group is on a carbon that's attached to 2 others. I know there's a ring to the left, but it doesn't matter. It's attached to a carbon. That's all that counts. So that is a secondary alcohol. And here we have a C double bond O, and the C double bond O group has a group to the left and a group to the right. So this is a ketone yet again, like it should be. There's 3 examples of this hard oxidation reaction. It's all you have to do to predict the products. I've also showed you 3 different examples using reagents on the arrow. In one form, they gave you H2SO or CrO4. In the other form, they've given you Na2Cr2O7 with sulfuric acid. And then the very first one that we did CrO3 with H2SO4. Again, chromium trioxide in sulfuric acid is one version that we can use. And then sodium or potassium dichromate, and this time we used sodium, with sulfuric acid was an oxidation. And then the other form, chromic acid. Full-blown chromic acid is what they wrote, H2CrO4. So once again, do not let it throw you for a loop. It's all chromium. You see chromium in all three examples, and it works the same every single time. So that's where this video is going to stop. Now in the next video, notice here we only did secondaries. So in the next one, we're going to focus on a primary. What do primaries do? And remember, I told you we could stop it at a certain point. So what do we use in order to stop the oxidation process from happening? So that's what you'll learn when you come back. I would say just bite the bullet, folks, and press play immediately after this one. You're on a roll. I know you're going to be oxidation pros, and you're going to be even more so because all of that material is going to be fresh in your head when you hit play immediately after this one. So come back and we'll talk about primary oxidations when I see you next.